So here we are given a velocity time graph where we have an object that starts at an initial velocity v0 and then it increases the velocity for a time t1, and after that in time it goes at a constant velocity. Let us try to see how the acceleration time graph and the displacement time graph of this body will look like. Before we dive into writing the graphs, acceleration time graph and displacement time graph, let us first try to see how the object is behaving through this graph. So we see that the object at time t equal to 0 starts off with an initial velocity of v0. That means that when t equal to 0, the object is already moving. And then for a time interval t1, the object increases in speed due to a constant acceleration. At time t1, it reaches a velocity of v1, and then it starts to go at a constant velocity after that. Notice that this means that the object has not stopped moving, it is moving at a constant velocity. Now let us try to draw the displacement time graph and the acceleration time graphs, starting with the acceleration time graph. So we know that the slope of the line in the velocity time graph will give the acceleration. Here we see that is some amount which is constant. So let us say that it is here. It will be a straight line, a horizontal line, because it's a constant. And then the acceleration jumps instantly to 0, which we can denote like this. So this is how the acceleration time graph will look like. Now let us draw the displacement time graph. So we see that the velocity has increased and that we have a constant acceleration, which means that our displacement will be a parabolic path. So let us say that it starts off at some displacement, x0 over here. So what's going to happen is that the object is going to undergo a parabolic path with respect to time like this. And once time t1 comes around, the object will continue to move in a straight line. So to summarize, if this is the velocity time graph of any object, then its acceleration time graph would look like this, and the displacement time graph would look like this. So for our next example, we're given a displacement time graph of an object, and we can see that the object starts at a displacement of 0, and then the displacement increases linearly to some position, x1. Then the object is going to stay there for some time, and then come back to 0 with an acceleration. So, and our target is to draw the velocity time graph and the acceleration time graph for this situation. Before we start to draw the velocity time graph and the acceleration time graph, let us first try to analyze how the object is behaving if it undergoes this displacement time graph. So we can see that the object is going to start at a displacement of 0, and the displacement is going to increase linearly to some displacement x1. Now we know that the equation for the displacement is given by x is equal to x0 plus v0t plus 1/2 at squared. The only way for the displacement to be linear is if the 1/2 at squared term is equal to 0, and that can only happen with a constant velocity. Now looking at the time interval between t1 and t2, we see that the object's displacement remains constant. That means that the object is not going anywhere. And finally, between the time intervals t2 and t3, we see that the object comes back to 0, but this time, unlike the previous situation between t equals 0 and t1, we can see that the graph is curved, which signifies that there is an acceleration involved. Let us start now by drawing the velocity time graph for the situation. So first, the interval between 0 and t1, we see that we know that the velocity is going to be a constant, and let us just say that it is here at some v0. And after that, the velocity will be going to 0 between the intervals t1 and t2, since the object is not moving. So that will be signified like that. And finally, the velocity will become negative because we are going in the opposite, because the velocity is going to be going in the opposite direction between t2 and t3, and the velocity will be increasing as we go from t2 to t3. So that will look like this. So this is how our velocity time graph will look for the situation. Now let's try to draw the acceleration time graph. And for the acceleration time graph, we can just look at the velocity time graph and analyze that. So we see that the velocity is not increasing between interval t0 and t1. Let's write t3 over here. Yeah. We see that the velocity is not increasing between t0 and t1. That means that the acceleration between this interval must be 0. And the same would be applied between t1 and t2, as the velocity is still not changing. However, between t2 and t3, we see that there is a negative acceleration, which is going to be constant throughout. So if we draw that, we will get a line that looks like this. For a final example, let us take a real-life situation where an object is going to start from rest, and then it's going to be thrown up, and it comes back to its initial position. So let us start by drawing the velocity time graph of the situation. So when I throw it up, I release it with a certain velocity, with a certain initial velocity, and that's going to be v0, and then that velocity will become 0 at the peak of its flight. This velocity change will be linear. So we start off at some positive velocity, v0, and then this velocity goes down to 0. It becomes, let's say it becomes 0 at some time equal to t1. As the object comes down, we see that its speed is going to continue to increase as it comes down, but this speed will be in the negative direction, so that means that the velocity will be negative. And it will come back to negative v0, as you will learn later. Now let us try to draw the displacement time graph of the situation. Actually, it's going to be y over here. So we know that our object is going to start at a displacement of 0. It could start on the ground, or in this case, it is starting on my hand when I throw it up. When it's thrown up, it's going to always reach a certain height. Let's call that height y1. And it's going to go to that height parabolically. So that means the change in displacement is, not going to be linear. It is going to also slow down as it reaches the top, as seen by our velocity time graph. So our graph is going to look like this at time t1. After that, the displacement comes coming all the way back down to where it started, which in this case was my hand, and it will also come down through a parabolic path. So, and this is how our displacement time graph will approximately look. And finally, we can draw our acceleration time graph. Through the velocity time graph, we can see that our acceleration is always going to be a constant, and that will always be a negative amount, as when you throw it up, the object is decelerating, and when it is falling back down, it is accelerating, but it is going in the negative direction. So our acceleration is always going to be some constant throughout the whole trip. And this constant, we will later find this out, is going to be the constant, the gravitational acceleration, g, which is approximately equal to negative 9.8 meters per second squared. After drawing your displacement time graph, velocity time graphs, and acceleration time graphs, it is always good to check whether the graph you drew makes sense using some mathematics. So one way how I like to do it is I like to compare the slope of the tangent line at a couple of points to see whether it matches up with all my graphs. And let me show you how. So in my displacement time graph, you can see that from time equal to 0 to time equal to t1, the slope of the tangent line is slowly decreasing until it reaches 0 at time equal to t1. And you can see that is exactly what's happening for the velocity. Remember that the slope of the tangent line in a displacement time graph represents the velocity. You can see that it starts off at some amount v0, and then it slowly decreases to 0 at time equal to t1. And between time equal to t1 and time equal to t2, we see that the slope will decrease even more to become negative, and as it approaches t2, it becomes more and more negative. And that is exactly what happens over here. Similarly, we can check our acceleration time graph. The acceleration is going to be given by the slope of this line in the velocity time graph. And since that slope is always constant, that means that my acceleration is always going to be a constant between 0 and t2. And you can see that that is the case. We can also check that it's negative because we can see here that the slope of the line is negative.